Chapter 2, Internal Energy, Work, Heat, and Enthalpy. Section 2.8, Isothermal Processes. Reversible and irreversible isothermal expansion and compression were studied in a previous section. Therefore, we will just briefly review these processes here. Example problem 2.8.1. Calculate the amount of work and heat involved in the following irreversible versus reversible isothermal processes. A. A 80-liter ideal gas with 1 bar pressure is compressed to 20 liters and 4 bar pressure by an external pressure of 4 bars. This is an irreversible process because the difference between P external and P is finite. W is negative integral P external dV. We plug in all the numbers, we get positive 240 bar liters. Because this is compression, the surroundings does work to the system. B. The same 80-liter ideal gas with the same 1 bar pressure is compressed to 20 liters and 4 bar. This time by P external is equal to P. This is a reversible process. Still, work is negative integral P external dV, but this time in a reversible process P external is equal to P. So we replace P external with P, and pressure is nRT over V because it's an ideal gas. We integrate 1 over V dV, which is the natural logarithm of V, and then multiply by negative nRT. The result is negative nRT times the natural logarithm of 4. We do not know the temperature, but we do know it's an isothermal process. So PV is equal to nRT throughout the entire process for the ideal gas. We still plug in all the numbers. We get 111 bar liters. So we have 240 bar liters in the irreversible process, 111 bar liter in the reversible process. Note that the system cannot be compressed if P external is less than P. So P external, has to be either P or slightly greater than P. Therefore, the lower limit of the compression work is achieved in this reversible process in which P external is equal to P. But again, they actually differ by a infinitesimal amount. When the system expands, the lower limit or the most negative of the expansion work is also achieved in a reversible process. So the reversible processes always provide a lower limit for the expansion work. At the same time, they provide an upper limit for heat in an isothermal process of ideal gas, because we know Q is delta U minus W, and delta U is delta PV plus delta KE. For an ideal gas, delta PV is always 0. For the isothermal process, the kinetic energy of the ideal gas only depends on temperature. When temperature remains unchanged, KE remains unchanged. Therefore, we have Q is equal to negative W. So in a reversible process, we get the lower limit for W, and then an upper limit for Q.